Our application of classification to matter leads us to the discovery of the existence of elements. And then by being rigorous and seeing how those elements combine together to form compounds, we discover some fundamental laws which John Dalton synthesizes together into a unifying atomic theory of matter. Now, having arrived at this theory, are we content that this is satisfactory in explaining all there is to explain about matter? Or is there even more fundamental information? Do these atoms themselves have some sort of structure that unifies them in their characteristics? Well, it turns out that they do, but the actual structure that they have is so surprising that no one guesses it. It comes from a series of experimental results, which forced chemists and physicists to confront their previous ideas and to adapt them to what these experiments have surprised them with. Now, probably the most significant starting out is the discovery of what's called cathode rays. Now, in 1654, Otto von Guericke has discovered how to create vacuum. He has invented a vacuum pump, and in 1835, Michael Faraday notices that when you apply a charge to this evacuated chamber, you get a glow. This is essentially a neon sign. And so the question is, what is that glow? Where does it come from? Well, this becomes even more strange. As later, in the 1870s, William Crookes, using a similar apparatus where we have this electrical charge in an evacuated chamber, discovers that as you further evacuate the gas in this chamber, the glow starts to disappear. It starts to become a little bit darker, and eventually the darkness spreads to the entire chamber. But at the same time that happens, you start to develop a glow at the end of the chamber. So what happened to our original glow, and why is there a new glow? Well, Johann Hittorf realizes that there must be a beam traveling through this tube. And so as you evacuate the air from the tube, when you have some air in the tube, that beam collides with the air and gives off that glow. But as you have less and less gas in the tube, then eventually it's able to travel all the way to the opposing electrode, and the beam continues and strikes the end of the tube and causes some glowing to occur. And so you can't actually see the beam, but you can see this glow, or you can see it striking air. And eventually, chemists start coating the end of their chamber in things like zinc sulfide and phosphorus in order to enhance the visibility of the beam. And so now there are two theories about what this beam might be. It might be made up of atoms, which have acquired charge, or it might be some sort of radiation like light. The identity of this enigmatic ray attracts the attention of J.J. Thompson, the British physicist. And he notices that a magnet put in proximity to the cathode ray will cause it to deflect towards or away from the magnet. This gives him an idea of how he can determine the composition of the ray, or at least something about it. So what he does is he uses an electromagnet to restore the straight path. So the magnet causes the beam to deflect, and then he uses these charged plates in order to push it back to where it ought to be. And because he knows how much voltage that he applied on those plates, then he can calculate the charge to mass ratio of whatever it is that's being deflected here. The mass gives it inertia, which resists the deflection. The charge makes it sensitive to the charge on the plates and the magnet. And so he can get that ratio based on how much he needs to get it back on track. And it turns out that this is 1/1800th that of the lightest known element, which is hydrogen. And what that means is that it cannot be made of atoms if it's 1/2000th the size of the smallest atom. And so it must instead be a new particle, the electron. On a completely different set of experiments, and not too much later, 1900, Henry Becquerel shows that you also get these results for a mysterious radiation called beta radiation, which is emitted spontaneously by radium. So if you have some radium in a storage vessel, it will just automatically produce this radiation. This image is actually from another substance that he also experiments with, uranium. And so the uranium causes some development on the plates. You can faintly see here that a Maltese cross has been placed in front of one of the pieces of uranium and blocks some of the rays. And so because these rays come from the atoms, and because they have the same identity as the cathode rays, then they must be made from the same thing, and the cathode rays must come from the atoms themselves. So they are made out of electrons. Well, it's well and good to know the charge to mass ratio on the electrons. We're very grateful to Thompson for that. However, we would probably like to know the actual charge and the actual mass, particularly because charge and mass are conceptually somewhat distinct. Now, the solution to the conundrum of how you would actually measure these quantities is figured out by Robert Millikan. This is a very famous experiment because it's so elegant and so insightful, called the Millikan oil drop experiment. What he does is he, first of all, purloins his wife's perfume bottle, and he fills it with oil, and he spritzes it through a charged screen, and in so doing, the droplets of oil presumably pick up some quantity of electrons. Some of them might not pick up any. Some of them might pick up 2 or 3 or 5. Others might pick up a whole bunch of them. That's undetermined. But once the droplet does pick up some electrons, it's allowed to settle on a charged plate. And this plate, Millikan controls the amount of charge on it. So he can calculate that charge. Now there's a force acting on this droplet. The force is gravity. Gravity is pulling it down. And the strength of that force is going to depend on the mass of the droplet. Well, that's easy enough to determine. He just looks at it through a microscope and he knows the density of the oil. So after he figures out the radius of the droplet, then he can calculate its mass, and then he knows the force of gravity, which means he also knows the amount of force that he is using to suspend it in air and cancel out that gravity. When Millikan calculates the charge in each droplet, what he notices is that each time it's always some multiple of this quantity, minus 1.6 times 10 to the minus 19 coulombs. So it would make sense if this was the charge on an individual electron, and so that's why he always measured some multiple of that quantity. And it turns out that he was correct. In fact, this is an accurate value for the charge on an electron. Because we know the charge and the charge to mass ratio, we can also get the mass of an electron, which he determines to be 9.1 times 10 to the minus 31 kilograms. And that's very light. It's 1/8000th the mass of a hydrogen atom. The picture of the atom that scientists now believe in after the cathode ray experiments and Millikan's experiment is they believe that we have these electrons, negatively charged particles embedded in the atom, and the atom is neutral, so it must be like a positively charged C, and altogether those charges cancel out. And when you form the cathode rays, you strip the electrons out of these atoms and send them shooting through your tube. This is called the plum pudding model because it's kind of like some plums embedded in a sea of pudding. Well, the investigation into the structure of the atom doesn't stop with the discovery of the electrons. And where it really reaches a turning point is in 1911, when Geiger and Marsden, under the direction of Ernest Rutherford, perform an experiment. In their experiment, there's this other kind of radiation. We already learned about the beta radiation, which is actually electrons, and is emitted spontaneously by things like radium. Well, alpha particles are another form of radiation, and they're very different from beta particles. Instead of having a negative charge, they have a positive charge, and they're about 8,000 times the mass of the electrons of the beta particles. And they fire this at a very thin piece of gold foil. So it's only about 400 atoms thick. And the result of doing this, what you would expect, according to the plum pudding model of the atoms, is that the alpha particles will travel and encounter these gold atoms, and they'll be deflected by the charges. But since there's both positive and negative charges in kind of a soup here, they'll be pulled towards negative charges and pushed by the positive charges on either side, and it will mostly cancel out. If there's randomly, one or two extra charges on one side or the other, that might lead to some mild deflection. And so you'll get a beam that's mostly all in the same spot with a few readings a little bit out in the edges. The actual results of this experiment are a stark contrast to what was expected. Instead of getting some very mild deflection, you actually get very sharp deflections. Some of these beams practically come back towards the emitting radiation source. And it's very surprising. Rutherford describes it as firing a 9-inch shell at a piece of tissue paper and having it bounce back and hit you in the face. The interpretation of why that would happen, if we are having very sharp deflection, since these are massive pieces of radiation, they must be striking large masses, which have the inertia to deflect them. And because they're being deflected, there must be some repulsive force there. So they must also have positive charge. So that's the conclusion. The atoms must have a dense positive nucleus. And we know that the nucleus is dense because a lot of these beams are still deflected slightly. So most of the time you miss this central nucleus, but very occasionally you hit it head on, and then you get these sharp deflections. So this elucidates the interior structure of our atoms. In further experiments, Rutherford shows that all atomic nuclei contain the hydrogen nucleus. That's the bare piece of positive charge in the lightest atom known. And so that's named the proton, and it must be its own particle, which has a mass of 1.67 times 10 to the minus 27 kilograms. For convenience purposes, we rename that and call it 1 atomic mass unit. That's a little bit of a lie. This is not exactly the same number because of the way the atomic mass unit is defined. For our rough purposes, though, we are essentially going to say a proton has an atomic mass unit of 1. We'll also redefine charge and say it has a charge of 1. And that's just very convenient. The electron has the opposing charge, so it has a negative 1 charge, and we can neglect its mass because it's so light. Rutherford also proposes the existence of a neutral particle called the neutron. And this particle turns out to have a very similar mass to the proton. It varies just a little bit, 1.675 times 10 to the minus 27 kilograms instead of 1.6727. But this is still close enough that we can set it equal to about 1 atomic mass unit. And so we aren't going to bother to differentiate between their masses for our rough purposes. Now, because it's a neutral particle, that makes it very difficult to work with experimentally. The positive particles, you can create a positive or a negative charge to attract or repel them, and same for the negative particles. What do you do for the neutral particles? How do you stop them from moving? Well, because it's difficult to work with those, it takes a while to confirm Rutherford's hypothesis, another 12 years. In 1932, James Chadwick finally confirms its existence. And so now this is our picture of an atom. It has a dense, massive, positively charged nucleus made up of the positively charged protons and the neutrally charged neutrons. And then it's surrounded by electrons, and the electrons have a lot of space. Now we're going to want to have a convenient way of representing all of our information about the structure of an atom. So we want to represent the number of protons, the number of neutrons, and the number of electrons. The notation which has been developed to do this is first you write the name of the element, and you use an abbreviated symbol for that. For example, Cl is the notation for chlorine. These are usually 1 to 3 characters. Then in the upper left, you write the total mass, and this is measured in AMU. Remember, we assigned both protons and neutrons a mass of 1 AMU. So this mass is essentially just going to tell us the total count of protons and neutrons added together. We also write the number of protons, and this is because we give the protons a +1 charge each. Then this is also going to be the charge on the nucleus. And so it's very convenient to use these units since these numbers tell us 2 things at once. And if we want to find out how many neutrons there are, we just have to take the difference, subtract the number of protons from the total number of mass units, and what's left over should be the number of neutrons. Remember, electrons, they weigh such a small fraction of the mass of these other particles that they're essentially negligible. So we don't bother to count them in our mass calculations. One other piece of information that we can include is the total charge on this atom. Now, for most atoms, they have the same number of protons, which have +1 charge, as electrons, which have -1 charge. And so it all cancels out and turns out to 0. So what we do is, for convenience, whenever it's 0, which is most of the time, we don't bother writing anything there. And it's only if it's picked up a positive or a negative charge that we actually explicitly include a term in that region. Okay, so if I give you one of these symbols and I ask you what particles compose it, let's say that we have gold here, which is represented by Au, and it has picked up a +2 charge, and its total mass is 197. So what particles make up one of these gold atoms? Well, protons we can just write down. So that's just listed here. If there's a 79 there, that means there's 79 protons, which altogether carry 79 charge. Now to find neutrons, we use this number in the upper left, which represents the masses of the protons and neutrons combined. So the mass of the protons is also going to be 79, since each of them have 1 AMU of mass. And we take the difference of the total, and that leaves 118 neutrons left over. Now the electrons, we need the total charge to come out to this number, this +2. And where that +2 comes from is adding the charge of all the protons. So there's 79 of those which have a +1 charge, and all the electrons, some unknown quantity with a -1 charge. So if we solve for x in this equation, move this term over to the left side, so we subtract that from 2, and then divide by this -1 to make it go away and get x by itself. Then x has the value of 77 electrons for this gold atom. Since now we know what elements actually are, rather than having simply identified the fact that they exist. We're ready for a more fundamental definition of what an element is. Our definition is going to be that an element is all of the atoms which have the same atomic number. That's the same number of protons. And an isotope will be any variation in its quantity of neutrons. So these are all hydrogen because they all have one proton in their nucleus. But this is an isotope with an extra neutron called deuterium, and this is an isotope with two extra electrons called tritium. And this is also considered an isotope. So there are 3 isotopes of hydrogen, and this is the way we write their atomic symbols. They always have Z of 1, but the atomic number varies because we have more nucleons contained. Now the question is, given that these are all hydrogen, how are we going to be able to distinguish them? This tool which we can use to identify isotopes is called mass spectroscopy. And where it starts is in 1886, Eugene Goldstein discovers a cathode ray which travels backwards. So instead of going from the negative terminal towards the positive terminal, it goes from the positive terminal towards the negative terminal. This is a very faint ray present going in the opposite direction. This is further quantified by Wilhelm Wien. He separates the positive ray and gets different components which vary by their mass-charge ratio. And what's really interesting is depending on what gas they started off with in the tube before they mostly evacuated it, they get different results. So this is the picture of the apparatus. So you have your gas particles, and you fire them between some charged plates, and then the detector, the gas particles are going to land on different points in the plate depending on their inertia. If they have higher mass, they're going to be able to resist this deflection more, so they'll change very little. And the particles with lower mass will wind up further down. And so you can use this to figure out the actual mass or the mass charge of the particles. If the charge is just 1, then wherever they land corresponds directly to their mass. In the present day, we've developed this technique to where we can use it to identify a whole variety of isotopes and even different molecules. The molecules we break into pieces, and the pieces, it's the same principle. Depending on where they land in the detector, we know their mass, and then we can start guessing how they would come together to form the larger molecule. So this is what they do in CSI when they're identifying a substance and where it came from and all sorts of information about it. But because it involves a lot of guesswork, it's a little bit more difficult in practice than they make it seem on the show in order to figure out all of those details. Now, when we're trying to report the mass of an element, say we have a sample of carbon that we've isolated from some source. We're not going to try and report the mass of every carbon atom, but those atoms are going to vary in mass since we have different isotopes. So what we're going to do for our sample is that we're going to report an average mass for those atoms. And we want it to be a weighted average. If we have a very high abundance of one particular isotope and very few atoms correspond to any other isotope, then we would like the average mass to be very close to the most abundant one. So the formula in order to do that, we just take the masses and we multiply them by their fraction. So this is just their percentage, except we don't multiply by 100 to make it a percent. We just leave it as a fraction. So if we have 50% of some isotope, we'd multiply by 0.5. And if we had 50% of some other isotope, we'd also multiply by 0.5. And 0.5 plus 0.5 adds up to 1. And so that gives us a total mass, which is representative, but the fraction that is representative depends on how much of that substance was in the original sample. This symbol is a summation sign. It's the Greek letter sigma. And so it just means that you calculate this mass times its fraction, and then now you go and do it for the second mass times its fraction, etc., etc., and you add those all together. This is an add everything together sign. Well, let's do an example. I have done my best here to depict the mass spectrogram of silicon found in the Earth's crust. So our signal, since we're dealing in fractions, can vary from 0 to 1. 1 is the largest possible fraction you can have of 100%. Now the masses which come up in our mass spectroscopy, we get a mass of 28 AMU, 29 AMU, and 30 AMU. So these are our 3 different isotopes. You can see that the mass 28 isotope is by far the most abundant. It makes up 0.221 fraction of the sample, which you can think of as 92.21%, and then a very moderate fraction of these other 2. So our question is, what should we report as the atomic mass for silicon found in Earth's crust? And before we start, it's always good to do some sanity checks on your numbers and sort of have an idea of what answer you want to get. So since this is an average, we definitely expect the number is going to lie between 28 and 30. If we get a number that's more than 30 or less than 28, we know we made a mistake in our mathematics. Also, since by far the largest quantity is the mass of 28 AMU, then we also expect that the fraction is going to be much closer to 28 than it is to 30. So let's see if we work it out and we get something that satisfies those constraints. So we're going to use our formula for calculating the average mass. We take the masses of the individual isotopes and multiply them by their fractions. And then this sign means we add them all together. So we start with our first isotope, multiply it by its fraction, second isotope, its fraction, third isotope, its fraction, add them all together. And the quantity we get when we do this is 28.109 AMU. And that's close to 28, like we predicted we would get, and it's between 28 and 30. So this seems like a good answer. Note for your significant figures that these are exact numbers here. So this represents an exact number of nucleons. We don't try to measure it out to 29.1 nucleons or 28.5 nucleons because we can't cut nucleons in half. So that has infinite precision and does not require us to truncate the sig figs in our measured numbers. So since these numbers, this one went out to the 10,000th place, this one went out to the thousandths place, and this one went out to the 10,000th place. So we expect when we add these all together, we're going to go out to the thousandths place.